2D projective transformation is describing the relationship between this plane and the floor plane. But what's the relationship between these two planes? It's formed the projective transformation. It's formed as the projective transformation. So what is the projective transformation? So the projective transformation is like if you have a camera over here, just imagine right now you have a camera and this is your image plane. This is your image plane, and that's your object space coordinate system. So in this case, you are taking a photo, and when you are taking a photo, this is called the central perspective projection, right? Frame camera is is following the central perspective projection. In Chinese, it's called 中央透视投影. Later on, we will talk about that in detail. So in this, which means that the light ray will concentrate to the perspective center. So you have a central perspective or a central perspective center like this. And then in this case, the transformation between this floor plane and this image space can be described with the 2D projective transformation. So this still abstracted, I know. So how about let's draw something like this? Imagine right now the floor plane, we have tiles, right? So in this case, if we have a floor plane as the very, very regular tiles like this, this is one image plane. This is one image plane. And imagine that is the floor, right? That is the floor. And right now, if I take a camera and if I take a photo, like with this direction, with this angle, and take a photo, and what would your image look like? What will be under your image? What's the shape of this?
Distorted a little bit.
Right. But
it distorted a little bit.
Distorted a little bit. Distorted like what?
Like a triangle shape? Like
Triangle shape?
not exactly triangle,
It becomes a triangle?
No. It's not.
Similar to triangle. And what's that?
Trapezium?
Triangle?
Trapezium?
Yeah, trapezoid. Trapezoid. So it should be something like this. Something like that, right? So, imagine again. So this is the floor, and then when you take a photo with, for example, this direction, and then this will be on your image. This will be on your image. Okay. So the 2D projective transformation, it can help you to describe the transformation between these two types of shape. Okay. These two types of shape changes. And this is called the projective, which is called perspective, central perspective. Right, 中央透视投影, central perspective projection. Right, so the 2D projective transformation is for the two-dimensional plane and two-dimensional plane and describing their coordinate transformation function. But these two coordinate transformation, these two coordinate systems, they need to have one relationship, which is following the central perspective projection relationship. And what is central perspective projection? All the frame camera, they are actually following this. This is the central perspective projection. So you can imagine that because when we are using the camera to take the photo, we have a central location for all the light ray to concentrate. So that's why it calls central perspective projection. In Chinese, it's called 中央透视投影, right? Because we have this perspective center has the other name, which is called 透视中心 or perspective center. Right? So central perspective means it's describing that perspective center. Okay. 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 Any questions on that? If not, then let me ask you a question. So basically, to summarize, these are the three coordinate transformation functions that we are going to discuss in this course. So these are the 2D to 2D coordinate transformation functions, and we haven't finished yet, actually. So when you have when you encounter any chance to select a specific coordinate transformation functions for your own work, and then how are you going to select so among these three, for example, which one do you want to choose? So when you are trying to decide which coordinate transformation function to choose, you need to consider what it can do for you, actually, what it can do for you. For example, let's say, if I have a square for and how can this conformal transformation help me to transform it? So, for example, if right now I have a square, and the conformal transformation can help me to transform this square to what other shape? Or to what shape? Diamond. Sure, diamond is basically, diamond. So your diamond is actually the square and just rotated, right? So it's still a square, right? If you look at it like that, so it's still a square. And so which means that it can transform it to another square. What else? Any other shape that the conformal transformation can help you to transform to? Is there any other shape that conformal transformation can help you to transform to? No. Right. No, there's no other shape that conformal transformation can help you to transform to. So conformal transformation can only help you to transform square to square. So that's basically what it does. But how about affine transformation? If I have a square, and what other shapes that I can derive by using affine transformation? What's your name? Angie. So what other shapes? In your opinion? You're not sure? Can you transform to square?
No, it won't be a square because you said this one, it changes
I mean,
the angle.
can it be a square? It can be a square, of course. It covers, for example, it covers whatever the conformal transformation it can do, right? So of course, it can transform to square as well. And what else? Deborah, in your opinion? Diamond?
With the longer width.
Longer width?
Yeah.
Okay, so what's the name for that? Rectangle. Rectangle. Alright, so from the square to rectangle, of course. Okay? So any other things? Any other shapes that I can do? Isa, you are drawing something in the air. What's that? Okay. This is called parallelogram. Parallelogram. I think it's pronounced like that. Or okay, so I think parallelogram, right? Okay, so good. So yeah, it can transform to that shape. Why? Because the affine transformation function helps you. It allows you to have two different rotation angle in the x and y axis. So you can do that. You can do that here. And also the diamond shape that along the diamond shape, of course, you can do that, of course. Right. So as you can see, the affine transformation function, it can help you to transform to many other shapes. Okay. So, but however, it has one limitation, which is the these coordinate transformation functions can only accept linear changes in terms of the x and y direction. It can only help you to have a linear change. Doesn't matter, it's a rotation angle, scale changes, shift is, of course, is a shift. But rotation, in terms of rotation and scale differences, it should be linear. It should be a linear change. So, which also means that it cannot help you to have this type of shape changes. So, as you can see, the 2D projective transformation, if we simplify this view, if we have a square, what's the shape it can helps you to transform to? Trapezoid, right? Trapezoid. It can help you to transform to trapezoid, teaching. Right? So that is not acceptable for affine transformation to do, because affine transformation needs you to have consistent and also linear change in terms of the x and y direction. So, but in order to transform to trapezoid, it should be you can only use a nonlinear function to do it. Okay, so that's the case. So what I'm trying to say is that if in the future you have two coordinate systems and you want to derive the coordinate transformation function between these two coordinate systems, and in this case you need to go back to the geometric changes that you need, and then and according to that choose the coordinate transformation function that you need, or that you need. So to summarize, conformal transformation can only help you to transform square to square. Affine transformation can help you to transform square to many other shapes, as long as they are linear. And 2D projective transformation is usually used if the two planes they have the central perspective projection relationship. So which means that it's a square to trapezoid relationship. Okay. Okay. Any question? Yes.
How about
Circle. Circle, huh? No, these cannot be transformed to the circle. Right, from the square to circle. No, it cannot be transformed like that. Right. You probably need other transformation functions to do it. Yeah, you need to use another transformations functions to do that. Right. Right. Any other questions? You need a very nonlinear transformation function to do that, actually. All right. So, but before we finish the class, actually, that's the 2D to 2D transformation functions. Let me just add one more thing. 3D to 3D. So there's a 3D to 3D coordinate transformation function. What we call the seven parameter.
Oh, I'm sorry.
Alarm? Really?
Yeah.
I need to see that.
No.
Is it
I
alarm?
took it off already. Took it off.
Really?
It is alarm.
Okay, I will let, because this is your first class, so yeah, I will let you go this time. But next time you need to follow the rule. Alright, so we have a 7 parameter coordinate transformation function for the 3D to 3D transformation. So what are the 7 parameters for? You can imagine. The 7 parameters, what should be included? 3 for what? 3 for translation, right? 3 for translation, or shift, Right, 3 for shift, X, Y, and Z. For the X, Y, Z shift. And what else? Scale. How many do you need for scale?
3.
3. So 3 for scale.
Yeah.
Then what else?
Angle.
Angle. How many do you need for angle?
Maybe it's also 3.
Then it should be 9 parameters just measure, right? So which is important? Which is more important? Scale and rotation. Which is more important, in your opinion?
Scale.
Scale. Scale. Scale. Anyone vote for rotation? Rotation. Only 1, 2. Only 2. All right. Why rotation? William. So, 5 for rotation. Come on.
I guess rotation will keep a shape most like the original shape.
Okay, most like the original shape. Okay, so what I would say, I would vote for rotation actually. So in my opinion, consider if you have three-dimensional coordinate system and you want to transform to another three-dimensional coordinate system, usually you may need more than 1 rotation angle, right? You probably need more because you have 3 axes. So supposedly you have 3 rotation angles that we defined before, the omega phi kappa. So we have 3 rotation angles in the coordinate condition equation. So 3 rotations. 3 rotations. And for example, but only 1 left. So that one is scale. Right, so which means that, which indicates you